From our work on the previous page, we now have a mathematical model of the sampling distribution of sample proportions. This model describes how much variability we can expect in random samples from a population with a given parameter. If a normal model is a good fit for a sampling distribution, we can apply the empirical rule to use z-scores to determine probabilities. Here we link probability to the kind of thinking we do in inference. We're kind of building our way towards inference here, making connections to probability models in probability and probability distribution. Probability describes the chance that a random event occurs. Recall the concept of a random variable from the module probability and probability distribution. When a variable is random, it varies unpredictably in the short run, but has a predictable pattern in the long run. Kind of like we were talking about, if this is the p, in the previous page it was 0.60, sometimes it'll vary widely, especially if the sample size is small, but it'll narrow in and most values will be right at p. Anyway, sample proportions from random samples are a random variable. We cannot predict the proportion for any one random sample, they vary, but we can predict the pattern that occurs when we select a great many random samples from a population. The sampling distribution describes this pattern. When a normal model is a good fit for the sampling distribution, we can use what we learned in the previous module to find probabilities. Recall probability models we saw in probability and probability distribution. We saw examples of models with skewed curves, but we focused on normal curves because we use normal probability models to describe sampling distributions when we make inference about a population. As we now know, we can use a normal model only when certain conditions are met. Whenever we want to use a normal model, we must check the conditions to make sure a normal model is actually a good fit. Now we'll summarize our general process for developing a probability model for inference. This is essentially the same process we used in the previous module for developing normal probability models for relative frequencies. Let's scroll down so we can see that. Okay. This looks complicated, but let's break it down here. The question here, in this top box, it says, assume that 60% of part-time college students are female. This is an example we've seen on previous pages of the same module. What is the probability that a random sample of 100 part-time college students estimates this proportion within 5%? Well, we see that the size of the sample is 100. That's a good thing, right? The larger the sample size, the more likely you are to be close to the actual population proportion of 60%. So let's develop a probability model for inference. Let's assume that we know a parameter value. Simulating sampling distribution, use simulation to collect many random samples from the population with assumed value. Make a histogram of sample proportions. Use relative frequency to estimate probability. So here we go. The relative frequency here is 0.64. The answer is probability that sample is between, it says within 5%. So if you're within 5% of 60%, which is what we're assuming the proportion of college students that are female, it would be 60% minus 5%, that's 55%, and 60% plus 50 or plus 5%, that's 65%. That's where they got those numbers here. The probability that the sample is between 55 and 65% female is approximately 64%. So they're just saying of all those random samples they took, they graphed them on the histogram, 64% of those random samples were within that range that they asked about in this question here, within 5% of the population. Let's see. The mathematical model for simulating, or for sample distribution, the center and spread is similar to the simulated distribution. So kind of compare, this is the one where we did a bunch of random samples through a simulation, kind of like we did on the applet on previous pages. It looks a lot like this mathematical model. Recall from module 13 that we can either use sampling or use a mathematical model to predict what's going to happen with sampling, I guess, or with mathematical model of sampling distribution. The center and spread are similar to the simulated distribution above this one. We'll use a normal curve if certain conditions are met. The area under the curve is 1, recall from module 13. So this is a probability model. The area under the curve is probability. That's what we saw in module 13. So if that doesn't sound familiar, maybe it's good to go review that. 13 information. Standardized model for normal distribution. Oh, wait. Oh, sorry, I forgot to mention. Here we were talking about a mathematical model that someone came up with. They came up with the area under the curve of 0.68, so a 68% probability that your values or your sample values will fall within between 55 and 65, which is pretty close to what we saw when we did the sampling, or someone did the sampling. Standardized model for normal distribution, so that we can use one normal model for different scenarios. We translated sample proportions into z-scores, just like in module 13 we saw. Use the distribution of z-scores and an applet or other technology to find probability. The area under the curve is the probability. So that's what they did, same value here, 0.60. If a normal model is a good fit for the sampling distribution, we can standardize the values by calculating z-scores. Then we can use the standard normal model to find probabilities, as we did in probability and probability distribution. The z-score is the error in the statistic divided by the standard error. For sample proportions, we have the following formulas. Okay, let's go look at those. Okay, so these are good. Maybe write these in your notes if you haven't already. We've seen them on previous pages, I believe. Yeah, let's see. Standard error. Okay, I think on the previous page. The standard error is the square root of p multiplied by 1 minus p all over n. So make sure you do that calculation inside the square root first until it's one number. You know, multiply p by 1 minus p, whatever you get from that, divided by n, and then whatever you get from that, then take the square root. Z is equal to, in the numerator, the statistic minus the parameter over the standard error. So we'll talk about that a little bit more. That's, in other words, the statistic is p hat with a little hat on it minus p over standard error. Okay, and then z, yeah, oh sorry. Another way to say that is p hat minus p over standard error, but standard error is the formula above. So we can replace standard error in the denominator with that actual formula, the very top one that they showed us there, over square root of p times 1 minus p all over n. That's all in the square root. So it's kind of a complicated looking thing. This z-score formula is similar to the z-score formula we used in probability and probability distribution. We describe the z-scores as the number of standard deviations a data value is from the mean. Here we can describe the z-score as the number of standard errors a sample proportion is from the mean. Because the mean is a parameter value, we can say that the z-score is the number of standard errors a sample proportion is from the parameter. A positive z-score indicates that the sample proportion is larger than the parameter. A negative z-score indicates that the sample proportion is smaller than the parameter. So, and then we'll look at this example here. Let's return to the example of community college enrollment. Recall that a 2007 report by the Pew Research Center stated that about 10% of the 3.1 million 18 to 24-year-olds in the United States were enrolled in a community college. Let's again suppose we randomly selected 100 young adults in this age group and found that 15% of the sample was enrolled in a community college. Previously, we determined that 15% is a surprising result, but now we want to be more precise. We ask the question, what is the probability that a random sample of this size has 15% or more enrolled in a community college? To answer this question, we'll first determine if a normal model is a good fit for the sampling distribution. Okay, we're going to scroll down and check that here. All right, we'll check the normality conditions. Yes, the conditions are met. The number of expected successes and failures in a sample of 100 are at least 10. We expect 10% of the 100 to be enrolled in a community college. N multiplied by P. Remember, N is the size of our sample. P is the population proportion. They said we're taking 100 students and 0.1 or 10% of them are expected to be enrolled, which is sorry, I was thinking, why didn't they give the equals here? 100 times 0.10 is 10. So we expect 10 to be enrolled, and then they move on. We expect 90% of the 100 to not be enrolled. Yeah, if 10% are enrolled, the other ones, 90%, are not enrolled. So those are the ones enrolled. And then 100, the sample, the sample size multiplied by P in this case, 0.9, because that's 90% should not be enrolled. That's 90. To expect 90 people to not be enrolled, about. Yeah. We therefore can use a normal model, which allows us to use a z-score to find probability. We'll first calculate the standard error here. So it's kind of hard to read. Maybe I can zoom in. Let's see. We can see it better. Need to clear out. Sorry about that. Clear this stuff so we can see better. Here we go. So standard error. Let's calculate that. The square root of p times 1 minus p. Well, p is 0.1. 1 minus p. As we kind of saw above, is 1 minus 0.9. That's 0.1. Oh, sorry. That's 1 minus. I was getting too excited and put the answer in my problem. P is 0.1. 1 minus 0.1 is 0.9. That's where they got this number. And then the denominator is n, your sample size, 100. Just type that in your calculator. 0.1 multiplied by 0.9, whatever you get, 0.09. Divide it by 100. Take that square root, you get 0.03. And then calculate the z, the statistic, which was the one they gave us, because that's what they're asking about. They're asking about what is the probability that 15% of my sample is enrolled in community college. So what statistic did they give you to begin with that they're asking about? The parameter is 0.10, and then divided by standard error. We just take that from the calculation we already did. So if you ever do this, make sure you calculate standard error first, because you're going to need that in the denominator of your z. I got 1.67. Okay, I'm going to zoom out now. Now that we got all that, all those ideas kind of nailed down, just making sure it all makes sense. We'll find the probability using the standard normal model. Okay, let's look at that. So here's a normal model. This is not something you would be expected to find. You know, some mathematician or statistician came up with this model, but that statistic they were interested in that they asked about, 15% or 0.15, where does it lie on this? It lies about here where this yellow bar is. Okay, we'll find the probability. The probability that 15% or more are enrolled, I think was the question. More is larger, so we'd be looking at this way. So remember that from module 13, that the area beneath the curve represents probability. So we're looking at what's the area beneath the curve from 0.15 or 15% on to the left. Because I believe after all this talk, I forgot what they asked, but I think they were saying that at least 15% of college students are enrolled. So 15 and higher is what I'm interested in. Oh, after all that math, it's easy to lose sight of what I was trying to do. You know, what was I trying to calculate? Oh yeah, what is the probability that at least 15% are enrolled, which is 15 or higher? Okay. So just like in module 13, we would, like they said, we wouldn't have to do this by hand, but back before fancy calculators and back before applets and computer programs, they would have to calculate a z-score like we did above. It was 1.67, and then look that up in a table, and then you would know the area under the curve larger than that or smaller than that if you look it up in a table of values that are standardized and always the same. The area to the left, that's not what we're interested in, I think. I think they said they want the area to the right, right? It was this guy. Okay. If they had said, what is the probability that 15% or less of the sample is enrolled in community college, then I would be interested in the one to the left, because those are the smaller values, less. But they didn't say less, they said more, I believe, if I remember right. It's been so long. So that's why we're interested in that one. Okay, let's scroll down a little bit. Now that we kind of understand what they were trying to ask and how it relates to those graphs. Okay. We want the probability that a sample proportion is 15% or more. So we want the probability that a z-score is greater than or equal to 1.67. The probability is the area beneath the curve to the right, 0.0475. Our conclusion is, if it's true that 10% of the population of 18 to 24-year-olds are enrolled at a community college, then it's unusual to see a random sample of 100 with 15% or more enrolled. The probability is about 0.0475, which is 4.75% if you move the decimal over to the right twice. And that's not super common. You wouldn't see that very often. Probability is a conditional probability. Recall from relationships and categorical data with intro to probability that we write a conditional probability as probability of A given B or probability of A vertical bar B. That was a while back. We write the probability that a sample proportion is greater than or equal to 0.15 given the population proportion is 0.10 as the probability that that the sample proportion is greater than or equal to 1.5, given that, so the thing that follows the vertical bar is something that you're given, something you already know that will affect the probability you're trying to calculate.